Good afternoon, ladies and gentlemen. First, I would like to thank the organisers for giving me the opportunity to participate in this conference in this rather unconventional way. I give you first a little introduction on the subject, then I will talk about fractal strings and fractal chains, before going over to measure geometric regressions, and finally giving you a little summary and an outlook. Right. The eigenvalue problem, we just consider a bounded domain Rn, which is in our case normally just R, and consider the Dirichlet eigenvalue problem. We are in fact looking for a spectrum encoding function, that is, a function whose zeros are the eigenvalues of the Laplacian under consideration. So what is a fractal string? An ordinary fractal string, such as defined by Lapidus and others, is in fact a one-dimensional drum with a fractal boundary. So it is a complete set of disjoint open intervals, and we are going to study the spectrum of vibrations of this kind of objects. So, a string has continuous mass distribution along a segment, and in order to define a matrix Laplacian, we are considering the discretized version, that is, a chain. A chain is an assembly of identical masses, or a monoatomic chain is an assembly of identical masses coupled by harmonic springs of stiffness K. Then, how do we construct a fractal chain? Well, we combine monoatomic chains with increasing basic frequencies in accordance with the construction of the underlying fractal set. And then we have a few conditions on the number of masses, but in the end, the spectrum of the corresponding fractal string is recovered for the limit of the number of masses going to infinity. The Laplacian of a fractal chain is a pretty simple Laplacian. In fact, it is a matrix where it's a block matrix where all the matrices are taken with multiplicity eta k from this set of matrices. And then, as I already said in my talk in Moscow, we can have the characteristical polynomial of the Laplacian for this fractal chain by this product of hypergeometric functions. And in the limit, we have given already this spectrum encoding function for classical fractal chains. But we are now going to a slightly different problem. Here we see a fractal chain, that is, in black, the intervals where we have vibrations, and in fact these boxes are the boundary. It's a fractal set, and the boundary, so we can say that the masses are infinite here. Now what happens if we let these masses be finite? This is the first step. I have not much results about that yet, but I will now present a few results if we concentrate the masses strictly on the boundary. The red line here is in fact a mass distribution of this kind of fractal string, while what we are considering now is the black line, that is, the mass is concentrated only at the boundaries of the fractal set. This leads us to a measure geometric Laplacian. If mu is a finite atomless Borel measure on 0, 1, a function g is called the mu derivative of a function f if we have this condition fulfilled. If mu is simply the back measure, then obviously this is just about a very normal derivative. And then we will consider the eigenvalue problem, dd mu of f prime equals minus lambda f with Dirichlet boundary conditions. We can give this also physical interpretation. In fact, well, the most important is that d mu is is equal to the mass density, linear mass density dt. So we have this problem again as stated beforehand. This is then the physical model. We model the measured geometric compression string, fractal string, sorry, by masses on the boundary of the underlying fractal set. This is the standard triadic Cantor set, but just as an example. Then we obtain the matrix formulation of the Laplacian, and it is of this form. We have very simple, well, almost diagonal matrix, standard matrix, where we have these factors Re, which are typical for the fractal under consideration, and this is not quite the truth, because this is just a stiffness matrix, and we have to multiply this by the mass matrix, that is, the masses of the different atoms on this approximation to the measured geometric string. But we will restrict ourselves now to the case where the mass matrix is simply a multiple of the identity matrix. In this case, we can obtain the scale polynomial of the matrix, characteristic polynomial of the matrix D, and well, it looks quite a bit complicated, but A, B, C, and D are just, well, polynomials. In fact, these polynomials. And then we can apply this to known sets, so we can give the, well, a degenerate case, the standard homogeneous string. In this case, all the Ri are equal to 1, and the scaling factor kappa is equal to 4m plus 3 to the square, well, whatever. But in this case, these polynomials are simply scaled and shifted Chebyshev's polynomials of the second kind, and in the limit where n goes to infinity, this simply will be the sine cardinal function sine of x divided by x, which is the spectrum encoding function of the standard string, the uniform mass distribution. Now, changing the Ri's a little bit. Well, this looks complicated, but it is not very complicated. The brackets denote floor function. If we use these values, then we obtain the spectrum encoding function for the measured geometric string. It has already been found earlier by Peter Arzt by a completely different method, but the first few coefficients can be quite simply re-extracted from our proposition before. The advantage of this is that in our formulation, with the polynomials and this expression for characteristic polynomial, we have a higher simplicity in getting the eigenvalues, although these eigenvalues are not quite as accurate as those resulting from the final function. They give us a very good impression on where to look for these. So, getting to the end of the talk, I present the unifying framework for the study of ordinary fractal strings and measured geometric fractal strings, which is quite new. We obtain generalized trigonometric functions encoding the spectrum of the considered fractal string, and I hope that in the future we can get to cases where the mass matrix is not simply a multiple of the identity matrix, and I hope to find a closed form expression for all these recurrence relations. Thank you very much for your attention. If there are any questions, don't hesitate to contact me. Thank you.